Good morning. We begin with the presentation of the summer school. Thank you all for coming here, for being here. We are very happy to organize this 5th edition of the school on high performance and disruptive computing on remote sensing. This is the 2nd edition here at the University of Santiago de Compostela. My name is Dora Blanco. Probably you all know me because we have exchanged some emails. I'm full professor here at the University of Santiago and researcher here at CiTIUS, the Research Center in Intelligent Systems. We are here celebrating the first day of the school. The last days will be in a different building at the same campus. We are opening the school, and with me is the director of CiTIUS, Senen Barro, who is a full professor here at the university. He was rector during many years. A few years ago, he can explain his experience as rector of this university, and he is the director of the center. He is fighting for financial support for all of us and trying to promote all kinds of activities here, like this one. So I give him the opportunity to participate in the presentation because he has supported us with money, with persons, and with all this marvelous building we are in. Thank you, Senen.
Thank you, Dora. And, it's my pleasure to welcome you to the CiTIUS. Let me just talk about the CiTIUS during no more than 5 minutes, I hope. But I would like to share with you some information and some figures related with our research center. The CiTIUS is one of the 5 singular research centers of the University of Santiago de Compostela. We are singular in the sense that we are considered excellent research centers and with a high potential of knowledge transfer to the society and to the companies of the results of our research. So we are more than 150 people. 30 of us are IPs, and close to 70 are PhD students, more than 30% coming from abroad. We have an A as a qualification. We are very proud of it because we obtained it in the last evaluation, because every 3 years, more or less, an external scientific board evaluate all the singular research centers, not just in the University of Santiago de Compostela, but of the whole region. And just 4 of us, 4 out of 10, have the A qualification. And this is important not just because it's the highest qualification, but we obtain money related with the qualification. So the regional government give us every year close to 1 million euros because we have the A qualification. And this is very important money for us. So our research is related with 9 scientific areas, green and smart computing and devices, so mainly microelectronics, smart chip design, and high performance computing. We have a very good research group in HPC. We are very proud of all of them, and we are very proud of you, Dora. You are doing very, very nice things. Other 2 scientific areas are related with what we call support for machine intelligence, so mainly machine learning and automatic reasoning. 4 intelligent technologies areas, virtual and augmented reality, language technologies, computer vision, and robotics. And the last one is trustworthy AI. So trustworthy AI is at the same time one scientific area, but is also the path that all the scientific areas must follow. For us, it's much more important the quality and the relevance of our research than the quantity. More than 3 out of 4 papers are published in Q1 journals. about half in D1, and we have raised during the last 3 years more than 21 million euros, which is a quite important amount of money because we are a middle-size research center. So we multiply by more than 6 the money we obtain from the regional government. More than 1 out of 4 euros comes from Europe, so our presence and our relevance in Europe is increasing every year, and we obtain a lot of money coming from ERC grants, which are the most important grants in Europe. Training networks for training researchers. During the last few years, we have coordinated for all Europe 3 of these networks, one related with smart chip design, one with explainability using language technologies. I have been the coordinator of this, of the director of this network, and the last one is related with the developing of language technology tools in order to fight fake news or hate speech on internet. We have a very close relation with companies. In fact, we have 2 university company chairs. One is, I am the director of one of them, is the application of artificial intelligence to personalize medicine, and the other one is related with smart chip design. And we are the center responsible of the developing of language technology resources for Galician. We have, as you probably know, we speak 2 languages. One is Spanish, but the other one, our own language, is Galician. And Galician is a language, unfortunately, with a very low level position if we talk about language technologies. So we want that machines, as it happens with English, with Spanish, with French, with German and many other languages, we want that the machines also manage, deal with the Galician as they deal with English. So we are doing a very hard work and spending a lot of money coming from the Spanish government, from the Galician government, and even from companies in order to develop corpuses, language technology tools, many things. And finally, we have started up 5 companies during the last 10 years. Companies that are related with our research, of course. And 3 of them are alive. 2 have died, unfortunately. And these 3 are related with process mining, with indoor location and guiding of people and assets using smartphones. And the last one is very, very recent, is related with chip design. And finally, as you know, because you are here, we also organize very important events. For example, last year we have organized the ECAI. The ECAI is the European Conference on Artificial Intelligence. It's the most important scientific conference in Europe and one of the most important in the world related with artificial intelligence. And in fact, more than 100 people came from all over the world to participate on ECAI. Well, just a final message. Our university is very old. It's one of the oldest universities all over the world. It was founded in 1495. So save some time, not just to walk around the city and to taste our amazing food, but also to know some of our historical buildings. The heritage of our university is fantastic, it's unique. So save some time to invest in visiting our historical buildings and also the old city. And no more, just enjoy this event, this fantastic event. Thank you very much, Dora, for organizing it here in CiTIUS, and enjoy the city. Thank you.
Senin is busy and he has to leave, and we continue with a short presentation of the school. I will present basic ideas on the school, and then the next step will be a presentation by the director of the Galician Supercomputing Center, CESGA, who is very relevant for us here, and he's also contributing to the organization of the school. The director had a different event, so we will arrive in a few minutes. There are very, very busy persons. As a presentation, we are going here, we are in the 5th edition of the school, and I'm especially happy to say that it's the 5th edition because it has been very hard to organize the different editions. We began with the 1st edition of the school 5 years ago, online, because it was 2021. The first organizers were, one of the first organizers is Gabriele Cavallaro, who is there and who will be participating. He was one of the persons who created this idea, and he organized the 3 first edition in Reykjavik, in Iceland, in the University of Iceland, a very, very nice place and very welcoming. I hope that you will have the opportunity to travel there because it's fantastic. Last year was the first edition here at Santiago, at this same building, at CiTIUS, and this is the 2nd edition. Every year the school follows more or less the same structure, different days with different topics, and I will talk a little about the different topics only to give an overview. Well, we are here at CiTIUS, as Senen explained perfectly. This is a relatively young research center, a medium-sized center here at the university, and we are in the Campus Sur, the South Campus, called the Life Campus at the university. Here we have different buildings, some for teaching, some for research, and you will have the opportunity to know another building called Emprendia, because the last dates of the school will be in a different building. Please stay connected to Slack, because the different relevant communications will be shared using our channel. And here I give you some spots of the program and some ideas, but please follow the information there. Well, as Senen has explained, we have different research areas at this center, and I have marked, especially in this slide, high-performance computing and Earth observation, because it are my fields, so I have to put in a bigger size. And in my case, I work here with different researchers. You will have the opportunity to know all of them. Basically, the main persons: Álvaro Ordóñez, Pablo Quesada, Alberto Suárez Garea, and Javier Fandiño, who are around here and have sent some messages related to the school, and will help you in all the needs you will have during the school. Well, we are working in this area with different PhD students who are also here participating in this school. In remote sensing, you all know obviously the concept of remote sensing. You work on remote sensing on from different perspectives, and probably you are interested in particular fields in remote sensing. Remote sensing allows us different and very interesting opportunities to know about meteorology, biomedicine, civil protection, climate change, and different topics. Most of them are very well financed by the governments at this moment. For example, climate change is very interesting at this moment. The prediction of natural catastrophes, that is very relevant too at this moment. And all this information is possible, all these applications are possible because we have information mainly from satellites and from other vehicles, from sensors on board, flights, but mainly from sensors on satellites. And we have a big amount of information that can be used for applications at different scales. We can have applications at a local scale, for example, analyzing vineyards here in Galicia that are it's a very common use of images obtained by UAVs, by drones. We can have solutions at regional scale. We have here an image of our region of Galicia. And we can also obviously have solutions at global scale. We can predict movements of people or changes in weather in different places all around the globe, because we have information from satellites and many missions that have opened the information to all of us. For example, the Landsat missions, other missions are promoting that everybody access to data. In some cases for free, in other cases not, it depends. But the policy of open source is at this moment a standard. We try to share our models, our data, trying to contribute to the knowledge. And basically, well, we have here some images of one of our projects with different flights over a region of a river, trying to analyze the vegetation of the river. But we can have remote sensing information from multiple sources, from satellites, from photographs, from radar, from sonar, or even we can mix or extract information from some records obtained in the field, persons who go to the places and obtain information to contrast the information obtained by the satellites. This is obviously an increased area, Earth observation. We have many and many data obtained by the different sensors, high-dimensional data, data with high complexity, because we have different processes interacting in the data that we capture when we capture information, for example, for a biodiversity environment. We have information that reflects effects of the weather, effects of the vegetation, effects of the human activity in the area. So we are analyzing complex data with high uncertainty, because the capturing the process of capture data is under different variable circumstances. So we have a problem that is a big data problem, or even beyond a big data problem. In this situation, during the last years, we all know the solutions that have been developed, and many of the solutions are based on deep learning, machine learning, deep learning. So we are aware of this situation. We all the persons that who are working in remote sensing at this moment are using deep learning solutions at one extent or the other. In our case, it's the same. We are developing different solutions for segmentation, for classification, for anomaly detection, for different processes. And these solutions are based on deep learning algorithms. But the knowledge of the deep learning algorithm is not very regular, because it depends on your profile. You can be physics, or you can be you have studied biology. It depends on the profile. So it's not easy to understand how these deep learning models work and how to extract the maximum relevance of this information. During the last times, we all use GPUs, because it's easy to use a deep learning model using one GPU, maybe two, or different nodes in a cluster, or in a supercomputer, it depends on your possibilities, or using resources in the cloud, it depends on the work, on the possibilities, on our profile. Well, we have discovered this situation a few years ago, and we Gabriele Cavallaro and me work in high-performance computing and remote sensing, and we found that it was very complicated to share with some students our findings, and it was complicated to exchange our knowledge with other persons in the field of remote sensing who were not using these infrastructures, these GPUs, these supercomputers, because the learning curve is perceived as very steep, and it's not easy for many of the users to use high-performance computing in general. Within this word, high-performance computing, we include, in this term, we include GPUs, TPUs, tensor cores, nodes in a cluster, a supercomputer, but we include different technologies, edge computing, quantum computing, neuromorphic computing, different computing paradigms that are relevant at this moment, blockchain, which is not reflected, no, is not included here, and all these technologies can help us, but how? What is the easy way of using these technologies? How we can interact with these technologies? It's useful for us, it's really useful for us, for our work, for our objectives. The answer is yes, it's useful, but we need to select the right tools, we need to select the right machines adequate in each circumstance to our research. So it's interesting to know all the possibilities, and this school will begin or will try to introduce you in some of the different technologies, computing technologies that are available for you. This school is basically supported by IEEE GRSS, the Society of Remote Sensing of IEEE. They have supported us. They are the main organizers of this school. We are part of this society, so I have to explain about IEEE. It's the largest academic and professional society. The number of members is very, very high. As you can see in the slide, we have more than 100 countries involved in the society, and in particular, GRSS is located all over the world, especially at this moment where most of the meetings are for everybody online, so it's at each country, and we have many activities all around the world inside the society. The mission is basically promoting science, engineering applications, and education related to geoscience and remote sensing. In the case of GRSS, the number of members is around 5,000 all around the world, and is divided in different chapters. You can join GRSS, it's easy. The cost for students is around 30 euros. I have read that there's a discount at this moment, so it can be more or less the half this amount. And why join the Geoscience of Remote Sensing? Why join the Geoscience and Remote Sensing Society? Because you can share ideas, enjoy discounts, attending different conferences, meet other communities, organizing meetings, access different contents that are valuable. For example, you can access information related to this school, and you can organize activities from the student or researcher point of view. In my case, I'm organizing this school because I am part of the society, so it's obvious a way of interacting with other persons who are interested in the same things like you, and a way of creating a global influence around the things you are interested on related to geoscience. So if you are interested, it's easy, just search Join GRSS and you will find information to be a member of the society. The GRSS Society is organized in different technical committees. The committee that is organizing this school is Earth Science Informatics Committee. Is this committee who is in this part, but the organization is in collaboration with the Quantum Earth Science and Technology Committee. Gabriele is chair of this committee and is sitting here and is part of the organization. But basically, from a formal point of view, we are part of the Earth Science Informatics Committee, but collaborating with other persons. The committee at this moment has different chairs. The main chairs are Manuel Maschi, Peter Roman, and Gabriele Meoni. Gabriele is here at the end of the room, and the secretary is Jerica Chrisman. These persons are trying to promote activities inside the committee with the objective of basically of promoting informatics related to remote sensing, trying to achieve interdisciplinary work in this committee. And the committee has different working groups inside. So this is very hierarchical, as you can see. We have a chair, different societies, because the number of persons is very high. And in this committee, we have different working groups. I have a right to myself. I'm here at this working group, the high performance and disruptive computing in remote sensing. The other chairs of this working group are Rocco, who is also here, sitting here. He was yesterday sharing an amazing lecture with all of us here. Iskia and Sudan. Iskia is from the University of Huntsville, Alabama. He's not here, but he will participate online in the school. And Sudan Ja from the University of Kathmandu in Nepal. And the other working groups are the databases remote sensing group. Kumar is here and will participate in the school too. And Sujit and Rajat will participate online on Friday. So as you can see, all the persons in the committee are working together and participating in the school, and even persons outside these working groups, as I told you before. The high performance and disruptive computing in remote sensing working group, well, this disruptive sounds very strange, but it's basically innovative computing, for example, is, more or less could be called also high performance and innovative computing in remote sensing. Basically, try to cover all the computing technologies that can be applied to remote sensing, including this not as new quantum computing paradigm that is evolving very quickly during the last years. The objective of the working group is clear, is to promote high-performance computing and remote sensing working in an interdisciplinary way. So if we are working remote sensing, as we are, we need to speed up the processes. We need to obtain as many as possible from our data. We need to process the data in a very efficient way, and we need computing resources to do it. So we try to promote this interdisciplinary research at different levels. And we have developed and develop usually different activities. I won't give a very detailed overview of the activities, but only a global idea. We organize webinars, podcasts, paper journals. For example, we have published a survey on different computing technologies applied to remote sensing. If you search my name or Gabriele Cavallaro or Manuel Maschi, you can find it in Google Scholar. And we organize different sessions each year in the IGRS conference. This year will be in Brisbane, and we organize a community contributed session on high performance computing and remote sensing there, where different persons send papers and present their research. We also have recorded last year different podcasts that are represented here. You will have this presentation online, and we can see here the YouTube channel of CiTIUS where these podcasts are. These are small conversations on different topics related to the summer school. If you want to know more, or you have to have an overview, an idea, a general idea of the topics of the school last year, of the 2024 school, you can see these are video podcast. So we have different conversations with Arthur, with Gabriele, with Manuel Maschi on different, with Arthur from IBM, with Thomas Brunsweiler from IBM, who was last year here with us. And we talked informally about how different technologies could be applied to remote sensing. We usually publish the results of the school in the IEEE Geoscience and Remote Sensing magazine, that is represented also here. And we participate in different workshops and tutorials. Well, this is the 5th edition of the school. At the end of the coffee break, we will take a photo, a group photo like this, like all these photos. These are from the different edition. The last one is above, was here at CiTIUS, and we have the other two. You can see that the number of persons is increasing year by year. And after the school, we will have all the material in a link. The link is included here to give you the opportunity to see this link inside the GRSS website to follow the videos and all the material that will be used during the school. And we arrived to the agenda of the school, finally. Well, we have 4 days. During this first day, we began with the opening with Senem Barroameneiro, and in a few minutes, the person who will be presenting his collaboration with the school and the projects ongoing will be Lois Orosa, the director of the Galician Supercomputing Center. Then we will have a coffee break here and a presentation by one of the co-chairs of the ASC committee, Gabriele Meoni, who will be working, who is working in edge computing for Earth observation. He will give a talk after the coffee break. And then the other sessions will be devoted to Google Earth Engine. We have here Izquierdo-Verdiguier and Eric Smit who will be leading the lectures, and we have theoretical lectures and also hands-on here at the same room, and they will answer to all your questions related to this Google Earth Engine I was trying to anticipate information, but I will say later. And this will be the day. At the end, we will have the social dinner. The information will be in Slack. We will be together trying to exchange, to interact, and to share a nice afternoon today. And after this, we will go to the next day. Wednesday will be devoted to quantum computing. And in this case, the persons who are participating are in the slide: Arthur, Alessandro Sebastianelli, persons coming from different places, from the Jagellonian University, from the University of Iceland, for the Jülich Supercomputing Center, for the University of Sanio, from IBM. The persons from IBM will participate online, but will be also participating in this session. And tomorrow we will have also a visit to the Galician Supercomputing Center to know the facilities of the center, and we'll have the opportunity to ask all the questions that we have regarding the center, because they have a quantum computer, a supercomputer, different computing facilities there. And in the field of quantum computing, all the hands-on will be on Qiskit, a framework for developing quantum algorithms and for simulating them or executing them on simulators or in real machines. And the last 2 days, Thursday and Friday, will be devoted to multimodal foundation models for Earth observation. These deep learning solutions that are very modern, that are at this moment, we have a very unique opportunity, because TerraMine, one of these foundation models, was released a couple of months ago. So we have the opportunity of being almost the first persons in receiving information and sharing with the persons really involved in the development of this model. They will be here, persons involved in the computing part of the model and in the development part of the model. So we will have here persons with all these profiles. Persons from IBM and persons from the Jülich Supercomputing Center. And on Friday we will continue, but in this case the different lectures will be given by persons from NASA and from the University of Huntsville, Alabama. Kumar is here representing them, but other persons will be participating online, trying to guide you in the hands-on sessions and presenting the role of NASA in the development of foundation models. It's a way of approaching the open science policy that is at this moment encouraging very with high intensity, and we have this unique opportunity to ask the persons really involved in the process of developing or using these tools. Please feel free to ask all the questions about all your doubts. If you consider that are interesting, ask. If you consider it's not interesting, ask too, because it's a unique opportunity to exchange with us. We will have also different poster sessions. The poster sessions will be during the coffee break, not today, the last 3 days in the other building. So during the coffee breaks, we will have the posters, 7 different posters each day. I don't know if 7, Pablo knows the details, 5? 6 per day. Pablo is in charge of this task, so he knows the details, and he will be sharing with you the information using Slack to know if you need to present your posters one day or the other. We will put the posters in the common place, in the place near the coffee break, so we can exchange and ask yourself and discuss with you if you want to share your interests with the persons who are here. Is a unique opportunity to talk to persons who are listening to. Okay, it's not very common, so it's try to take profit of this opportunity. And the posters will be all the day, the whole day in the same place, so we can see them there. For lunch, today will be here, the last 3 days in the school where we are teaching informatics science. We will go together, so will be easy. We have the social visit, the social dinner today, the visit to Galicia Supercomputing Center tomorrow, and on Thursday we have organized a very short visit to the old town, because as Enen said, it's worth to spend a few hours walking around, and it's take profit of the opportunity. And thanks to all the persons and institutions involved in the organization of the school, IBM, Google, Microsoft, Amazon, to the agencies, space agencies, NASA, ESA, to the universities involved here, la Università degli Studi di Sanio, the University of Iceland, Jagellonian University, Boku University, to all the persons and institutions that have worked very hard here, the persons of my research group here, Gabriele Cavallaro, Vito Pravil, who is in charge of the web page and part of the communication, and all the persons involved, because this is a joint effort. And now we will go to the next presentation. As I said before, CESGA, the Galician Supercomputing Center, is very relevant for us because he has resources that we use very frequently, and they have dedicated effort and money to this school. Lois Orosa is PhD director of CESGA, and he has been researcher during many years. He's researcher at this moment too, and he has worked in different fields, and he will present. I have here your profile because it's not easy for me to remember all your research interests. Memory systems, hardware security, machine learning, microarchitecture, storage systems, processing in memory, different topics. And if you want, come here. I give you.
Okay, thank you very much. Thank you, Dora, for the nice introduction and for inviting me to give this talk. It's my second time in this school. Last year I was also here with similar talk. I read the talk a little bit. I don't know if many of you repeated this year the school. Maybe you can raise hands if someone repeats. One person, yeah, I know you. That is cheating. You are the local ones, so that's nice. Okay, yeah, tomorrow you will have the opportunity to visit our center. That is in the same campus. It's like 200 meters from here, I approximate. And yeah, and I will give a brief introduction on what we are and what we do here. So we were founded in 1993. I was not there, and in 1993, I just arrived 3 years ago, but I'm trying to keep up. We are placed here, and we depend on the regional government and also in the Spanish National Research Council. And our mission is to contribute to the advance of science and technology via research and application of high-performance computing and communications. We offer services, supercomputing services, to more than 1,500 researchers. Yeah, we collaborate with many projects and institutions. We are right now more than 60 people. We are growing. We have several hiring processes ongoing. And we have a broad variety of technical and research staff, like physicists, computer scientists, telecommunications engineers, mathematicians, etc., etc. And most of our departments do research or provide support or services for researchers like CiTIUS, for example, right? Or other research groups in campus, in Galicia, and in Spain. And in Europe as well, actually. We belong to the Spanish Supercomputing Network. This network is part of a unique science and technology infrastructure. And inside of this network, we are the second largest supercomputing center after BSC and after Barcelona Supercomputing Center. And we provide basically services to the national and international research communities. So this network launches some calls regularly, and so scientific projects can apply. These are evaluated scientifically, and if they are approved, they have the resources on some supercomputing center in this network to execute the project. Our culture from the beginning was always to collaborate. We are a very collaborative institution, so we have collaborations with many institutions. And our main goal is to advance science and research that eventually might have a positive impact on society. So we carry out research ourselves on diverse topics related to computer sciences, collaborate with other research groups, and also very important, we provide HPC resources and services and support to researchers from other institutions. Who can use our infrastructure? So mainly our main users are Galician universities, the Spanish National Research Council, but also other research institutions from Galicia, from Spain, and from Europe, and even international, that collaborate with us or with some institution from our region through a collaborative project or something like that. Okay, I will talk now about some of the classical infrastructures that we will see tomorrow in the visit. Well, before that, as I said, we are here since 1993, and at that moment, we have the most powerful supercomputer in Spain. It was a BP 2400 that was ranked 148 in the top 500 list, right? Through the years, we have several supercomputers. We entered in the list in 2003 again with the Superdome, and again in 2007 with the first finished array in the position 100. So we have a large history of installing and maintaining supercomputers here. The current supercomputer is Finisterrae 3. We have is in total more than 22,000 cores, almost 160 GPU accelerators, A100, more than 100 terabytes of aggregated memory, more than 350 terabytes of storage in SSDs, InfiniBand, emulators, quantum computer emulators, etc., etc. We are in the process of designing the Finisterrae 4, so this will be outdated soon, next year actually. We also have storage systems, well, with an aggregated storage of more than 33 petabytes of storage, have high capacity lustre-based storage system. We have tape libraries and other systems, right? We also have more resources, hardware resources. We have cloud infrastructure that is growing over the years. Right now, and the last update was in 2021, and at that time we installed more than 10,000 cores dedicated to this cloud infrastructure, more than 24 terabytes of memory, and more than 3,000 terabytes of storage. We also have, it's not here as well, but we also have some big data infrastructure dedicated to big data. Apart from computing resources, supercomputing resources, infrastructure, we manage the Galicia Science and Technology Network, called CESGA, that basically provides with access to internet to universities like this, universities from Galicia and other research centers. So meaning if we are down, all the universities will be down, will not have access to the internet. During the shutdown in the 28th of April, we were able to maintain the infrastructure up because we have some diesel generators and so on, but yeah. Was not a big deal because of our backup, energy backup, for example. So we have also, we are on quantum technologies. We are in both quantum computing and quantum communications. On quantum computing, in quantum communication, we have a quantum link, a QKD, quantum key distribution link between CESGA here in Santiago and Vigo Quantum Communication Center in Vigo. It's more than 100 kilometers of distance, and we are working on extending this link down to Portugal. We are just trying to figure out how to do it. We also have on premises some quantum communication lab of continuous variable QKD. You can see a picture there. It's a very simple lab. We are updating it continuously. And what about future infrastructures? As I said, next year we'll have new infrastructures. We will have also a new building, a new data center actually in the 4 kilometers from here, more or less. It will not be here in the campus, but will be in Santiago. And we'll host our main infrastructures so we can free our current building for hosting more people. And yeah, and this building is currently in the process of, we are building it. Well, the building didn't start yet, so we didn't put the first stone yet, but yeah. We have until June 2026 to do it, so we have to be very quick. You have to put some pressure on the constructors, but yeah. Hopefully we will do it on time. Our main problem is that we have until June 2026 to build the building, but also to have the machines inside. So yeah, it's even more challenging. We have in total around 56 million. That is a budget of 47 plus taxes. This includes a classical supercomputer that will be a supercomputer like with very AI, with many AI capabilities. Probably we have many GPUs or similar or dedicated hardware for executing machine learning workloads. Then we will have some investment on quantum computing as well. We will update our current quantum computer. And we will also have some budget for storage and so on. So in total, 56 million that will update our hardware infrastructures. And this will hopefully happen in 2026. It has to happen in 2026. Our quantum infrastructures. So quantum technologies, well, Dora already introduced a little bit about quantum, but just to give a little bit of an overview. So what is the potential of these technologies? So the potential is having a new internet with unbreakable security, with QKD technologies, with quantum communications, solving problems that are intractable with classical computing, with quantum computers, solving very challenging problems with low energy consumption, potentially. This is not proven yet, but hopefully we can work on this regard as well. Sensors with extraordinary accuracy, this is quantum sensing, and understanding complex quantum systems. That's why this technology for us is strategic, and this is strategic in our center. We, as CESGA, we also are leading the Galicia Quantum Technology Hub. That is basically a collaborative effort in the Galician region around quantum computing, quantum communications, and quantum sensing to have a common strategy and to identify opportunities for funding. We have regular meetings to identify these opportunities, to perform common actions, etc., etc. So our region is aligned in the strategy for quantum. In our center, we have several infrastructures. We have quantum computer simulators. These are basically classic computers that are able to run quantum algorithms. So we have several emulators or quantum computer simulators, a quantum learning machine from Atos of 30 qubits, although we reached 38 qubit simulations experimentally, one of our researchers did. We also have the Fujitsu Quantum Emulator, FX700 plus MPI QLux, and other simulators that are open source. We have a quantum random number generator from the company QSight. We are working on improving the interface that was a little bit primitive to give an easier access to the QRNG. And this technology, the hardware technology, basically is based on a patent from Marcos Curti, that is a researcher from Vigo, from the Galician region, here in the Vigo Quantum Communication Center. And users can already access it since a long time ago. And then we have our most famous quantum infrastructure, that is the QMIO, and it's a 32 superconducting qubit quantum computer that at the time, and I think right now as well, is the superconducting quantum computer with more qubits on at least South Europe, as far as we know. Maybe today is not the case. I didn't check the numbers, but at the time of installation it was. This is how it looks inside. These are some pictures of the actual hardware. This is our picture from a photographer that came to our facilities to take these pictures. And basically, this is mainly custom made for us, as many of the quantum computers that are existing today. Basically, this is manufactured by Oxford Quantum Circuits. It's provided by Fujitsu, but is manufactured by Oxford Quantum Circuits, OQC. It has some Quaxmon technology, some QPU of 32 qubits. And basically, this was the first of this class installed by Oxford Quantum Circuit. So we have a long time putting this computer to run correctly, and we are still improving it. This is how it looks. You will see this tomorrow, basically, because it's closed in a barrel that is it has vacuum inside. Yeah, and as you probably know, a superconducting quantum computer, it has to operate to very, very low temperatures in the range of millikelvins. So that's why this has to be very protected. Actually, these plates that you see here, they are used to decrease the temperature, and the QPU is on the bottom. So yeah, tomorrow you will see this. On the left, you see the cryogenic system. On the right, you will see the control electronics that basically consist of FPGAs. Each FPGA controls one qubit. On the left, you will see. Well, tomorrow they will explain you on site better. This is just some electronics. Basically, what the FPGA does is emit a signal to the qubits and then read the signal back. Basically, this has to be very precise, and it's very sensitive circuit. So I appreciate if you don't touch the computer. Okay. Here is like a record. Well, this computer is open to the community since more than 1 year ago now. So we have regular calls. You can submit your projects. If you are from abroad, the best way to access is through a collaboration with us or with some of the research institutions in Galicia, like CiTIUS, for example. Right? And yeah, basically, researchers can submit the project, and this project is evaluated. And if it is positively evaluated, then we will provide resources to execute the project. As I said, this computer is working from more than 1 year and open to users from 1 year. And since it's open to users, the temperature was under 70 millikelvins constantly. So in the top, I don't know if you can see the scale, but on the top is 17 millikelvins, and the bottom is 15 millikelvins. So it's pretty stable between 15 and 17 millikelvins, the temperature. Okay, I will talk now about some research and research and development projects that we are developing, or research and our research interests, right? So apart from providing resources, we are a research center, and as I say, we collaborate with many institutions. Our main research lines are high-performance, secure, and efficient computer systems and big data, quantum computing, quantum communications, earth sciences, life sciences. Here we have projects about climate, for example, in earth sciences, and in life sciences, like in drug discovery and so on. Applied machine learning or educational technology. These are some of the topics that we are interested in. For example, we do climate modeling. Specifically, we do numerical simulations, application of artificial intelligence technique to study future change in moisture transport and temperature anomalies. Also, we do numerical simulations to predict energy production from offshore wind farms, as well as losses induced by wind farm interactions to inform an increase in offshore wind energy production. That is a key technology for achieving net zero carbon economies globally. Related to this, we provide services and collaborate with the Galician weather forecasting services. So the prediction of the weather forecast is calculated at CESGA daily, twice per day actually, And we collaborate in research with them as well to use neural networks to better predict the climate and the weather forecasting. This is called Meteo Galicia. We also are participating in the Copernicus initiative, the Ocean Forecasting Service. That is the Earth observation component of the European Union's space program. And basically what we do in CESGA is calculating the simulations on the sea in the Iberian Biscay Ireland area, basically. We also, in the health space, we are currently working on One Health data spaces. Basically, a data space is an abstraction in data management that aims to overcome some of the problems encountered in a data integration system. So a data space is defined as a set of participants or data sources and the relations between them. So we are working on constructing a demonstrator, basically, built on CESGA that will be used by many use cases here in the region of Galicia. In the slide you can see some of these use cases, right? So, for example, to choose one, for example, the brilliant is the Sarcopenia Observatory and automatic analysis of MRI images. And this, there are many use cases from different institutions, mainly, for example, the Sarcopenia Observatory is from the Sanitary Research Institution. We also collaborate with the Galician Public Health Administration, specifically with the Fundación Galega de Medicina Xenómica, that they perform genomic analysis. And last year, I think this is not updated. I think it's 40,000 genomic analysis last year. That is, yeah, they were done here in CESGA, right? This group is led by Ángel Carracedo. Related in the sanitary area as well, we also worked on the Sinfonia project that is basically that is defined as the radiation risk evaluation of detrimental effects from the radiation exposure of patients with lymphoma or brain tumor, and not only patients but also medical staff. And the goals of this project were to develop dose estimation tools using AI or other computational tools, research on individual sensitivity to radiation, develop a novel patient risk evaluation tool, etc., etc. On the area of applied machine learning, our bigger project is in collaboration with a private company called FINSA, that is the largest and oldest manufacturer of chipboard and MDF in Spain. That basically what they do is transform products derived from wood. And the project basically consists into optimize together the production line using machine learning techniques. And we have been working together for 7 years, and we have learned a lot on this very practical case, and they were also very so they achieved very good results. So they were able to optimize a lot their production line. On computer architecture, we are working on new microarchitectures to make processors more efficient, basically more high performance, but mainly more energy efficient. Faster, more efficient and secure main memory systems, especially DRAM, but also storage systems and other memory technologies like PCM, for example. Analysis of security of hardware components of computer systems and mechanisms to improve hardware security, and proposals of cutting-edge architecture such as, for example, processing in memory or a specialized accelerator for genomics or from artificial intelligence, convolutional neural networks, and LLMs. Regarding quantum computing, the vision that, so in our center, we currently are working mainly on quantum algorithms. Probably in the near future, we will start working more on the hardware side as well. But the vision is that I think this is shared by most of researchers nowadays, that probably quantum computers in the end will be accelerators of certain kernels in a similar way as GPUs are accelerators today. So, because basically all quantum algorithms need a classical part. At least they need initialize the qubits and read the results. So at least these two parts have to be classical. So inside of quantum computing, our interests are hybrid algorithms, parallel quantum circuits, quantum machine learning, benchmarking, integrating quantum computing in HPC, quantum communications and QKD, and so on. Some example of collaborations. This is a collaboration with a beer manufacturer called Estrella Galicia and with Fujitsu. That is international, and basically this is this project was to search for active molecules. Basically, is to understand how some molecules react to flavors or something like that. I'm not involved in this project. That looks very cool, and yeah. But yeah, we have some interesting results here. There is some paper published. And we also are developing a distributed quantum simulator. The current state of this simulator is that we have classical communications between QPUs. We have the noise from the real QMU last calibration files. We have generic noise and so on, right? So yeah, basically this is the infrastructure. This is a project that we are working in the context of a bigger national project called Quantum Spain. We are also working with CiTIUS in high-performance quantum computers, specifically on QPU integration in OpenCL for heterogeneous programming. That is a standard programming framework for accelerators, and almost independent of the hardware. Yeah, so Andres Gomez and Tomás from CiTIUS are working on this project. And that's it. Some takeaways. So we are the second large supercomputing center in Spain. Have some large infrastructure, and next year we'll have even a larger infrastructure. We are very interested, and we are on quantum computer and quantum communications. We have the first quantum computer installed in Spain, for sure, and the most and the largest number of qubits in Spain, for sure. The other quantum computer right now installed in Spain is the Barcelona Supercomputing Center quantum computer that has 5 qubits. And also we have a quantum communication link with VIGOC, and that is actually one of the largest we have in Spain. We also do research and collaborate with researchers from Galicia, from Spain, from Europe, and also globally, right? We have some collaborations globally as well. And yeah, we usually collaborate through European projects or research projects related on the main topics of computer sciences in general, HPC, quantum technologies in general, right? And we provide HPC services and support to researchers. This is a key aspect of our center as well, right? We do and help other researchers to improve their research. And we are hiring, so we are interested in motivated researchers, students, technicians, quantum computing, computer architectures, experts on AI, HPC, bioinformatics, climate, life sciences, etc. We have some openings in our website, and in the next few months we will open more positions. So stay tuned if you are interested. we will be very happy to see you apply there. Yeah, that's it. Thank you very much. If you have.
Good morning, everyone, and thank you for attending this guest lectures on edge computing for Earth observation. And we discussed about advances and challenges in applying this computing paradigm to Earth observation. Quick words about me. I'm Gabriele. I'm Innovation Officer at the European Space Agency. I work in the Advanced Concept Study Office and in the PhilLab. And I'm also co-chair of the Earth Systems, Earth Science Informatics Technical Committee of the GRSS. My topic of interest are related to edge computing for space, AI for Earth observation, and quantum computing. And the learning objectives of this activity are related to this. Basically, at the end of this lecture, I hope you will be able to describe edge computing, at least the main motivation to apply AI on the edge for Earth observation, describe modern payload data handling units, and have some knowledge related to the main hardware platform that you can use, and also describe the main challenges in edge computing in space and current research trends. So first, we will describe very briefly what edge computing means and why we think it would be a good idea to apply it for space. Then we will discuss application of AI in space and of edge computing in general. We will give you a brief introduction about the hardware, and then we will describe the technical challenges and the current research trends, at least the most relevant ones. And then we will give our conclusion. So let's start from edge computing. I think most of you know what cloud computing is. Very easily, you have a lot of sensors that can be cars, mobile phones, cameras, that bring a lot of raw data in the network, and then you have a distributed computing infrastructure to process them. So this computing paradigm works very well, but it has one limitation, that is the fact that when you increase the number of nodes in the network a lot, the scalability might be difficult because of a lot of raw data that you bring to the network itself. So one approach to mitigate this problem is to add some server or edge processors directly close to the sensor. We talk about edge computing because we move the computation or part of the computation at the edge of the network itself, so very close to the sensor. And of course, this is not substituting cloud computing, but is integrating cloud computing, because you can pre-process the data and send only the relevant information to the cloud, where you can process them even further and with more computing capabilities for sure. So what about space? To understand why we are talking about edge computing, we need to start from the approach on which the current Earth observation mission are based on, and we talk about the so-called bent pipe approach. So here you have, I have to say, the old schematics of the Sentinel-2 missions, because now there is a Sentinel-2C as well, but okay, it doesn't matter, it doesn't change. So as you can see, according to the paradigm, the satellite acquire all the data, and then they can transmit the data when they are close to the ground station, the rod depths that you can see. And only when they are in line of sight with the ground station, they can send the data. I mean, this is not exactly true, because Sentinel has also other approach, but this is true for 99% of the mission. And also, as you can see, the orbital period of Sentinel-2 is actually 100 minutes. So I want to ask you now if you see any limitation in this approach. Don't be shy. Well, if you don't, we can try to think about it together. When we talk about bent pipe, we are talking about a system that is designed to send a lot of data to Earth from the satellite itself. But as you can see, I was showing before, the satellite needs 1 hour from an acquisition in the worst case to send the data to the ground station. So it's not very fast. Also, you are sending all the data, no matter of the quality of the data, on the interest of the data. So if you use the schematics that I put here, do you think there is a way to have edge computing to improve the system? Well, those are the sensors. The ground segment is actually in the cloud. Yes, the approach to have edge computing is moving the computation on board the satellite. So that's why we talk about edge computing in space. The paradigm is a bit different, but is not substitute for what we have today. It's complementary. Let's say you start from a satellite here that acquired the information. Let's suppose you monitor an area with a fire. With AI on board, you can produce the fire map. And since you are sending a very small piece of information, there are some satellites for communication where you can just send the map of the fire with the coordinates, and they can send it very quickly to the end user. So, and we are mostly using AI, not necessarily deep learning, but artificial intelligence in general to do this. Why this is because it's nowadays the state of the art for many applications, and also, especially when we talk about deep learning, the hardware is very versatile and reconfigurable, so you can have the satellite to be used for different applications. The advantages is that you have a much higher autonomy in the system itself, is much more responsive because you can send the information very quickly to the end user, and also data efficient. And now we will see over the lecture how this advantage enable new application. Of course, again, is not replacing what we had before, is complementing. You will still send all the data if you want to the Earth, in case it's needed, or when it's needed, but you can also do edge computing in case you want. Okay, I want also to talk about cognitive cloud computing in space. Especially if you go around the ESA website, you can find these words. This is, let's say, an extension of edge computing. So imagine to have a lot of satellites with computing capabilities in space, not only Earth observation satellite, but also spacecraft in orbit services and whatever. Then you can use edge computing to process the data, but you can use cloud computing, so having a lot of satellites communicating together and having a cloud in space. That's why we are talking about cognitive cloud computing in space. And in this lecture, I will limit to edge computing, but what I'm saying is also relative to cognitive cloud computing in space. It's important to mention that when we talk about edge computing on the satellite, you will see is a big word, and there are mainly two places where you can apply AI on board the satellite. Satellites are composed by two main elements. One is what is called the platform. So let's suppose again you want to have a mission to acquire to monitor fire. Then the platform is the part of the satellite that is more or less agnostic from the mission itself. What the platform does cares really about to have the satellites on the right orbit, to monitor the telemetry, detect and isolate faults. Is not really related to the commercial and scientific missions goals of the mission itself. And the main element, the brain of the satellite, is often called onboard computer. And then you have one or more payloads that are the part really related to the scientific missions. For instance, in the example of the fire, is really what it process the fire, store the data about at observation day, and so on. And when we talk about the processing element that you have on the payload, is not called onboard computer, it's typically called payload data handling unit. Why I'm telling you this? Because of course edge computing might be relevant to both. You can use it at the platform level to do fault isolation and recovery, or on the payload to process the data. And of course today we will limit the exploration to the payload, but it's worth knowing that also the other application exists, especially when you see edge computing apply on the onboard computer and not on the payload. Okay, now we can discuss a bit more about application of AI in space. So one, of course, is the low latency early alert systems. As I told you before, you can process the data on board, and as soon as you get, for instance, you monitor the fire with small delay, you know immediately to be a fire because you have detected it on board. So if you have a way to send information quickly to the Earth, and I told you that nowadays we have relay satellite for which you can send information quickly, you can build low latency early alert systems. So for instance, you can detect volcanic eruptions or you can provide early alert for disasters in 10-20 minutes from the detection, not from the inside, not from the on-site, but it is from the detection of the disaster itself. Also, you might have other more surveillance and civil security application like maritime surveillance. For the same reason, you can detect maybe vessel, dark vessel, and so on, and send information very quickly. There is also the possibility to reduce the data, as I was explaining at the beginning. One example that was tested on one mission called FISAT-1, that was the first mission using deep learning on an AI processor on board the satellite. What you can do is filter in the clouds. When you have optical imagery, the clouds will more or less obscure 50% of your imagery, because that's the presence of cloud on Earth, averagely. So that means you could save 50% of your bandwidth, or you could at least prioritize your downlink. So if you use AI on board, you can detect the clouds, and then decide which part of the image, or you can decide how to compress the image, and so on. There's always the question whether people want to do this in scientific missions. Regardless, if you want, the technology will allow you to do it. There are also commercial applications. Let's suppose to have indeed a cloud in space where you have satellites that can be also tasked in terms of acquisition. You could ask one or more satellites to acquire on different area, and then what you could do is process the image on the cloud, and then if you find something interesting, tasking another satellite immediately for another acquisition. So you will have an enhanced way to acquire information that also may be a very nice service for civil security and other application indeed. So yes, that's also another application of edge computing. And talking about enhanced acquisition system, something that is currently under research is the so-called TPNQ. So how many of you know what the revisit time of a satellite is? Raise your hands. Okay, not many. So the revisit time is the time that the satellite needs to process the same point on the Earth. And this time decrease when you increase the swath of the satellite, that is the area that the satellite is monitoring. Of course, the higher is the area the satellite is monitoring, the less paths you need to scan all the Earth. The problem is if you increase the area too much, then it's very difficult to have a high spatial resolution, because the same pixel is sparse over a bigger area. So you could decrease the swath, but then you have higher revisit time. Well, edge computing could allow to have both, in the sense that what you can do, you can have one satellite with high swath width scanning your area, and when you find a target event that you have for which you have not enough resolution to detect what you want to detect, but you might have at least you might believe there is something of interest, you can flag this area and ask another satellite with much higher resolution and lower swath width to cover that area. So in this way, you can have both high resolution acquisition and lower revisit time at the same time. So you can extend this idea also to complementary sensor, like multispectral, hyperspectral, SAR, optical, and so on. So you could really enhance the acquisition system thanks to the fact that you have AI and autonomy on board. Of course, to do computing, you need to have hardware, and it's very important to discuss about what kind of hardware you can use to do this kind of computation. But before describing this, let's play a game together. Let's try to understand what could be interesting metrics to evaluate hardware. Okay, one is quite easy. It's the so-called computing power or the performance. So basically, how do you measure? Well, you can have general indicators that are not really specific to the application. For instance, floating points per operations. Or you could use the benchmark. I don't know if you ever heard about Drystone or others. You launch in on your hardware. You monitor how long you take. Those are standard algorithms, and then you tell that my processor took 3 seconds to run Drystone, for instance. Or you could have application-specific indicators. For instance, if you want to do the inference of AI, one indicator is the latency. How fast I can do the inference, or the throughput. How many images I can process per second. Why is important? Well, because for instance, if you remember about the application for low latency means that you need to process fast. So one limitation is also how fast you can process on board. So hardware performance are important. There is another one, I guess. It's quite popular.
How much energy it costs?
Exactly. Energy efficiency. So how do you measure it? Well, Joule, of course, energy per operation if you are really into the hardware, or then you can have energy per inference, for instance, if you want to relate to a single application. Why do you think is interesting for satellite application? Because satellites are energy constrained somehow, in the sense that, of course, the bigger they are, the less they are constrained, but in general, there is a limited capability to bring energy from the solar panel, and also depends on the orbit itself. So, in general, the energy that you have limits the area that you can process, and so the area that you can monitor. So, if you are not energy efficient, you risk to pass from a data downlink approach problem to an energy problem in monitoring the area efficiently. There are also thermal constraints. The power that you produce, if you don't dissipate it correctly, and if you produce too much, will increase the temperature. And as you probably know, sensors, the thermal noise is directly, the power spectral density is directly proportional to the temperature itself. So temperature is a big problem on satellite, and you need to monitor correctly. So energy efficiency is a key element on this. Quick question, do you know the difference between power consumption and energy consumption? Because we hear both. Yes. Let's say the energy is the average power multiplied by the interval that you monitor. On the satellites, you might hear both, because typically you measure the energy, the average power over the orbit. So you fix the delta T, basically. So sometimes you talk about power constraint, energy constraint. Somehow they are related, but having energy constraints is different from having power constraint. Power constraint means that on that instant you cannot dissipate more than that power. You have both typically. But energy is typically what limits overall the orbit, and is typically what you hear more. There is another one that is probably less relevant for other applications. That is radiation. So I will not go into the detail of physics, even because I'm not an expert. But you have three main effects, we can say. The first one is called the single level effect. What it is? Well, you know, radiation is a problem because you have charged particles mostly in space that hit your hardware. When it happens, the radiation will trigger basically a glitch in the digital electronics. And for those who knows about T-setup, T-hold, and digital electronics, they might know that the electronics might trigger the glitch. And this might make switch some of the bits in your computation. So if you have, for instance, a number represented in complement 2, and you have a 1 bit flipping, like the sign, you are changing the sign to one of the number that you have, and you might end up in wrong computation. Or even worse, if you trigger one of the bits of the representation state in a state machine, your system can go banana, because you are in a state that doesn't exist. Of course, there are a lot of tricks in the way you represent the states and so on, so to avoid this, but just to let you know that these are one problem that you might have. Typically, you might resolve it by resetting your system. But there are other things, like a total ionization dose. When you expose your hardware for a long time in space, you start accumulating charge. Charge is accumulating on the transistor, and after a while, your transistors basically are in a permanent on or off state, and they don't work as a switch anymore. So your electronics will be done over a while. Typically, you can measure this by using tests, but it's more or less an indication how long your hardware can survive in space. Unfortunately, there is something even worse, a so-called single event latch-up. So I will not go into the detail of what a latch-up is. I will tell you that when you have a very high energy particle hitting your hardware, a positive feedback loop might start increasing the current in your transistor until they burn. And something happens very fast. So you might have also a single event destroying your hardware. So why this is important? Of course, because it strongly affects your system reliability in space. And some hardware are more reliant than others, depending on the way they are fabricated. Okay, there is another one. This is naive. It's cost. How do you measure it? Well, in euro, typically, or dollars. We can say there are two main elements in cost. One is so-called non-recurring engineering cost, and they are all related to everything that you need to spend either to procure the hardware before start selling even one element of the hardware. the manpower to develop something. The hardware itself or the software is part of non-recurrent engineering cost. The facility that you need to produce the hardware or the computer are part of this. And then you have the recurrent engineering cost. So what is proportional to the number of devices that you're going to sell or to use, basically. And then you have sites and mass. These one are very important to space because they are related to the launch of the cost and also on the feasibility to design your system. If you want to have a CubeSat, for instance, you cannot have something that is very big because it will not fit. So those are also quite important parameters that you have. Okay, talking about the hardware, we have microcontrollers. I think more or less all of you know what a microcontroller is. Microcontroller integrates basically a microprocessor with RAM and typically peripherals like GPIOs and other things. It's a fixed hardware because the hardware is fixed, and then changing the software, of course, you execute a different applications. This is quite naive. They are general purpose. That means they're very flexible. You can use it for a lot of different applications, but also mean they're not optimized because they're not optimized for anything. So they're very flexible. Typically the performance is not great and the energy efficiency is not great either. It's lower than a GPUs, for instance, in terms of energy consumption, but not in terms of efficiency, not necessarily. Also, the development time is quite slow because once you know how to program the microcontroller, you do it quite easily. So the non-recurrent engineering cost is low. And also, typically, anche the recurrent engineering cost is low because microcontrollers are not that expensive compared to other devices. Radiation tolerance depends on the technology and on the design itself. When do you use it? Well, typically it's very rare that you use microcontroller for nowadays AI on board. That's because typically the performance are not great, you have something better. But if you have a very small CubeSat, for instance, where you cannot fit more devices than what you have, you might have a single device doing the onboard computer and data processing, and in that case you might use a microcontroller typically. Field programmable gate arrays, or so-called FPGAs. So those are programmable hardware. What does it mean, programmable hardware? Well, differently from what you do for a microcontroller, when you program an FPGA, you design the hardware. So the programming microcontroller means writing the software or the firmware. Programming an FPGA means describing the hardware that you want to have. So what you're going to build is a hardware dedicated to your application. That's because FPGA has programmable connection and switch and interconnection and also programmable logic on it. You also have, to make things a bit more complicated, system on a chip FPGAs that couples FPGAs with microcontrollers. Why you do that? Typically because it's not necessarily true that having a dedicated hardware leads to better performance. Some algorithms, like algorithms with a lot of if-else state machines, are very easy to be mapped in software. So for some application, it might be better to have actually both. The flexibility is typically quite low compared to other applications because changing application might require to redesign the hardware. The performance and the energy efficiency is quite high. Indeed, they are typically used for high data rate application on board. For instance, if you want to do SAR data processing, typically you will find an FPGA because you can, in addition to the AI part, in case you want to use AI, you will find all the possibility to integrate FFT and all the blocks that you need to do SAR data processing. This is just an example of application that you can do with them. The development time is quite high. I can tell you that I did a PhD on FPGAs, and to me, to do a design from scratch for a single AI model with some colleagues took 6 months. So GPUs or microcontroller is much easier for sure, but performance are quite good. So for application where you really need something like that, they might be very good. Radiation tolerance can be quite high, also for commercial applications, for commercial FPGAs, not only the space FPGAs. Nowadays, there is so-called high-level synthesis. So there's the possibility to synthesize the hardware from the Python or other high-level languages that will design the hardware for you. Of course, you lose a bit in performance, but will save a lot of time. So this is also a trade-off that you might want to explore if you need to use FPGAs. And nowadays, all the main FPGA producers have tools also dedicated directly for AI, so that can even improve the trade-off. Then we have edge graphics processing units, or edge GPUs. Well, I guess you know GPUs. They are massively parallel hardware optimized mostly for computer vision and data flow processing. They are very flexible, not as microcontroller because you cannot fit everything, but they are way more flexible compared to an FPGA for sure. Energy efficiency is quite bad, typically, compared to FPGAs and others. The development time nowadays, especially on some FPGAs that support CUDA, in some GPUs that support CUDA, for which you have the libraries, it's more or less comparable to CPUs. For other FPGAs, it might be more difficult. The recurrent engineering cost is quite high typically, because the price of GPUs, is, as you probably know, especially if you're into gaming, is quite high. The non-recurrent is not that high because the development is not that difficult. The radiation tolerance is typically very bad, except when you have radar GPUs designed for space. Why is very bad? Because GPUs are very large typically, and it's like particles hitting a device is more or less when you try to hit a target with a DARF. The bigger is the target, the easier it is to hit it. No, and FPGA and with GPUs is the same. Since the hardware is very big, they collect randomly more charge compared to a microcontroller or an FPGA for its design itself. So that's not great for space application typically, but of course there are a lot now attempts to have radar GPUs in space. Why GPUs might be interesting? Well, I will challenge you to do the training on an FPGA of an AI model. I mean, it's possible, but of course it's very challenging. GPUs are way flexible and allows you to do the training. Is training on board interesting? Might be, we will see later. So, and in general, allows you to develop cloud application in space. That's why they might be very interesting for space applications. There are also other devices, like application-specific integrated circuit that I'm not mentioning today because you don't see many for AI, but you have a class of commercial ASICs dedicated for AI. Sometimes they're called TPUs, sometimes are called VPUs. What they are chips designed to do AI inference typically, or some of them AI training, but mostly inference. They are very flexible until you don't move from the AI application. The performance are typically very good. Also, the energy efficiency is very good. And the cost is typically lower compared to FPGAs and GPUs. That's why they are quite interesting for space application. And they are typically used for inference on CubeSat, also microsatellites. So, I don't know if you ever heard about nanosatellites, means 10 kilograms, something like that. Microsatellites above 100 kilograms, just to give you. And of course, the bigger is the satellite, the easier it is to fit hardware on it. Okay, this is more or less what is interesting about the hardware. Now what we can talk about, okay, edge computing is very interesting, but is that easy? Well, no. There are so many challenges in applying edge computing in space, and now we are going to describe at least some of them. Well, first of all, I told you, you need to have communications. Otherwise, even if you detect something on board, but you don't have a way to send it very quickly, it doesn't change much. Okay, you can filter the data, you can prioritize the downlink, but you will get minutes, so you will still need hours to download the data, basically, from the acquisition. You might have radiation, I told you that, thermal problems and power constraints, because we already discussed, but there is also another big problem nowadays, is limited dataset availability, in the sense that, especially when you have new sensor on board, you never have a very representative data set of what is going to happen on board. And today we are focusing on these two elements in terms of challenges. I want to start from the last one that I mentioned, the so-called domain gap problem. Have you ever heard of that? So you have a domain gap when you train your AI model on a source data set, and then you are going to deploy it in your operational scenario, in our case on board the satellite, on a data set that features some kind of domain shift. So your application, your data distribution on the domain set, the target data set will be different from the source. And what kind of problem can cause the domain shift in Earth observation? But for instance, different operational conditions. You have data set for training only in daily light and you want to use your model during nighttime. What you're going to have there is a domain shift because you're not sure the model will work. Okay, maybe you can do some data augmentation, but you might have some domain shift. Well, another problem that is not really specific for onboard is a problem, I guess, in general for Earth observation, is when your data set is not really representative of your operational scenario. For instance, contains limited geographical areas, you have not enough samples in your time series, you train on a forest and then you test on a desert. Is it going to work? I'm not sure. This is a problem also on board because you might not have the data for all the area when you're going to release. No, maybe you have trained your model in a certain area, but then you deploy the satellite all over the world. But you also have problems more related to the onboard scenario. For instance, the unavailability of target data at training time. You have a new sensor, and you want to train an AI model. How do you do it? Well, you can wait the sensor to be the mission to be deployed, to be commissioned, then you need to collect all the data, to label them, and to do the training. And then probably half of your mission is gone, or some months at least. So it's not a great idea. The idea will be, okay, in the meanwhile I develop my mission, I want to train my model and then to deploy it. So one thing that you can do, you can try to emulate your sensor starting from other imagery. That's what, for instance, we did for the FISA2 Orbital AI Challenge. But as you see on the left, those are some emulated imagery. On the right, you have the real imagery. This is one example of FISA2 that we got. As you can see, there is this kind of grid in the image itself. I don't know if you can appreciate from there. This is stripe noise. You have some non-idealities in your onboard processing in your data that will make your data distribution different. And it's even worse because the noise can also degrade or drift. So you compensate the noise nowadays, and then in 2 days, 3 days, 1 month, depending on how lucky we are, the data distribution is changed enough to make the prediction unreliable. That's a problem that you have. And I can tell you that here, what you see is level 1. That means, I don't know if you're aware, you're familiar with the processing level of the Earth observation data, but the raw data that you are, typically, what you really acquire is very different from what you use on the ground to do your deployment. And raw data are typically not available in many missions. And so when you want to deploy your onboard pipeline, it's very difficult to emulate exactly what you're going to have without having the raw data. You need to start from other difference, but then you cannot emulate noise. And so at the end of the day, you will end up emulating something that is different. And also, you never know, for instance, the entity of the noise, of the registration, the lack of registration, and this will create a domain gap problem. And this is also exacerbated, as I was saying, by the fact that the raw data are often not available in Earth observation. So typically you don't find the level 0, you find the level 1. Nowadays we are trying to push a bit, you find some people releasing the level 0 for some data, but the raw data are typically not available. Okay, how can we solve this? Well, first of all, at least in space, for edge computing is quite a limited problem. You don't find many research, but the first approach that is more or less the one that nowadays everyone is using it, they train a model before on emulated data, they test it on board, they might work or not. For instance, in FISA1 work very well, FISA2 not really. And then what's happening? You need to fine-tune the data. So you need to foresee when you design your mission that part of your mission will be needed for your application to be fine-tuned. So you download the data, you label them, you retrain, and then you test it on board until you are happy with your performance. Of course, it's the easiest way. It's probably the most reliable because you have control on the performance, but it's not the most, let's say, automated or smart one. You might have in-orbit domain gap adaptation techniques. For instance, there are some techniques that are explored for which you can somehow measure the domain gap. there are metrics that allows you to measure, to estimate how the performance will degrade based on the image only, or by using some kind of internal metrics. For instance, you take a network, you throw away your head of the network, you take the body, and you use the internal features to measure the quality of your image, as you do in generative AI typically. Or you can directly measure it by doing the inference, but that's not the smartest ways. And then what you can do, you can retrain. That's why I was mentioning GPUs before, on board to fine-tune your model, typically using some kind of unsupervised techniques. There is also another one, currently under exploration, but you don't find a lot of citation, at least in edge computing, because they're very hard to deploy, is actually foundation models. As you know, foundation models are pre-trained on a massive amount of data, and because of that, they might be intrinsically more resilient to domain shift. Of course, the onboard deployment is tricky, so there's research on it, but you don't find much at the moment on this. I was mentioning also energy constraints. Energy availability fixes is again the maximum area that you can process, as I was saying before. So data used on the ground typically are strongly post-processed, like the level 1C, level 2A. This is because you want to give this data to the end user, and you want the end user to spend time to use the data, not to clean the data. Okay. The problem is bringing the same processing level on board is not easy because it's very computational intensive and also very slow. Can be also more computational intensive than the AI itself, depending on what you're doing. And the question that we have is, do we need it? Can AI process directly the raw data? Of course, as I was saying, it's a bit of a problem because we don't have the raw data, but we managed to get some raw data from Sentinel-2, not because it's the most interesting one in terms of onboard, because you cannot do onboard processing, but that's because of what we had. And we wanted to try to test for thermal anomalies on patch classification. So thermal anomalies can be volcanic eruption, wildfire, and so on, and see if you can create a map. How Sentinel-2 raw data look like? Okay, Sentinel-2 is a multispectral push broom sensor. Multispectral means that has 13 bands, at least the level 0, visible, near, infrared, and SWIR ranges, and is a push broom. Push broom means the satellite pass, acquire over a certain area. Due to the parallax needed to split the light in different bands, the bands typically are not registered, so they don't look exactly at the same area. The acquisition lasts 3.6 seconds on an area that at level 0 is called a granule. So this is the building block that you have at level 0, let's say, the piece of the puzzle to create your all word acquisition, basically. So just to give you an idea on this band's lack of registration, these are 3 bands on the first acquisition. Then when you acquire the next one, you will see that there is a bit of overlap on the different bands. That's because the bands don't look exactly at the same area. And if you mosaic them, band 2, 3, and 4 on a single acquisition, on a single granule, you will get this. So they are not overlapping correctly. So that's how the raw data look like. So processing might be challenging. In addition, you have no radiometric processing except for bands equalization on Sentinel-2. So that means you might have dark pixel, a bit of stripe noise that in Sentinel is more or less correct, and so on. Classical bands co-registration techniques are quite computational intensive. I mean, you have 2. One is a geometric model. You know more or less how your satellite is done. You know the attitude, and by doing some metrics, you manage to register the bands. Or you can use computer vision, like SIFT, AI, why not, and so on, to find, identify matching key points, and then to understand, to estimate what is the shift. You can clearly see these 2 bands are one a bit up and one a bit on the side. But we managed to build a raw data set called TROS, Thermal Hotspot in raw Sentinel-2 data, made only of 3 bands. That's because that is more or less what you need to detect thermal anomalies. If you want to download and play with that, you can take a look. You can take a look at the QR code and play with that. And we tested our onboard processing techniques. So first of all, what we did is starting from the bands and applying a course registration. So what we did, we calculate what is the average shift on the raw data over the data set, and we shift all the bands without doing any key point matching over always with the same shift for every acquisition. Of course, the registration is not going to be perfect, but you will see it's good enough in many cases for doing this. Then we have a general purpose embedded processor, one of the AI chips I was mentioning before. We crop the image in different patches because they cannot fit in the memory, all the image together, all the granule together, and we create the map. White, sorry for the misalignment, means no fire, red means fire. We can take a look visually at the results. Of course, there is a full paper with all the characterization, but I'm more interested here on the quality of the results. As you can see, some of the patches, they might look wrong, but if you zoom in, the AI model is very good. It's actually detecting the patches there. So that means it's possible to detect fire detection, do fire detection on the raw data, simply minimizing the pre-processing. And we tested this in collaboration with Ubotica, that's a company providing hardware, on what they call the Cognizant 6 board, on one of these AI VPU, AI chips processor. And what we got is a latency to do the full process, 2010-2000 on the device, plus the registration, on 1.8 seconds. That is half of the time that the satellite needs to produce the granule. So it's a real-time processing. And also the average power consumption is only 5.5 watts. And mostly is because you need a Raspberry to keep the AI chip alive. So just to tell you that at the end of the day, it's possible to process the raw data for some application, of course, and you might speed up the pre-processing a lot. Okay, I'm concluding my lecture here. I just want to mention some stuff. Just to give you some information about the PhilLab. We are located in Ezrin. We are a division in Ezrin doing disruptive innovation. So what we do, we really test we are the only, probably, reality in ESA trying to do the analysis from blue skies idea from really entering into the marketing. And we have, as you can see in the image before, a lot of visiting researchers that we accommodate to conduct research together. So why I'm talking about this? Because we are very active in collaborations, and especially on this topic, but in also other topics like foundation model, quantum computing, and so on. And there's always the possibility to be hosted at the PhilLab as visiting researcher. If you are interested to be hosted in Ezrin in Italy and collaborate with us on this topic or another topic, take a look at the QR code. Where you can see the collaborative innovation network. That is basically the network that we use to do knowledge management and to engage in collaboration. So if you are interested, take a look there, or don't hesitate to send an email, and for which we are happy to discuss possible project in collaboration. I also want to profit to do a bit of announcement. We are now launching in the coming days a new challenge. Is a challenge related to the AI, is not related to edge computing, is related to monitor and to provide a response to earthquake. This challenge is basically in collaboration with the International Charter Space, a major disaster that takes care of using Earth observation data to monitor, to provide a response to disaster itself. In this case, we are doing with earthquake. The charter is typically in charge on doing using Earth observation data to provide this kind of response. And in this case, we are applying the challenge will be related to providing and mapping earthquake damages to building on earthquake imagery. Why it's interesting? Because of course it's very important to do it very quickly and to automate the process, especially to provide a quick response after the earthquake. That's why AI might be very interesting. So if you are interested in this kind of challenges, take a look. It will be announced in days. You are getting soon then the real official announcement. And this is more or less what you're going to do with the challenge itself. So detect really damages on the image itself, on the building itself. To be announced soon, basically on the AI for your website or PhilLab challenges. So if you are interested, don't miss it. Sorry, I copied one slide more. I also put some reference on the materials that you can see about that you can read about all the topics that I discussed. I want to close. I hope it was not too long, and if I still have some time, I would be happy to take some questions if there are.
I don't know how many of you know the application of Google Earth Engine. Okay, seems not too much people. It's good, then a lot of people are going to learn something. So I'm in Izquierdo, I'm working in Boku University. I'm a Google Developer Expert on Earth Engine from 2022. And I'm going to introduce you what is Google Earth Engine and what we can do with Google Earth Engine during this talk. This afternoon we are going to go more in a practical session. We prepare an introduction and some examples. And I would like to ask you also, how proficiency do you feel on Python? Good? Yeah? Because you will see during the lecture now that there are different options to work with Google Earth Engine, so I need to decide which option I'm going to present it today. As most of you tell me yes, at least with the hat and with the thumb, I'm going to go in that way. So I'm going to show you how we can work with Google Earth Engine in an easy way, in a very easy way. We are not going to install anything in our laptops. If you wanted to go in that way, I will give you the resource and information of that, but we are going to go in the easy way. Well, as I commented, I'm Emma, he's Eric. He's going to help me in the practical part, in the practical session. And you can see here in a very small picture a when I work with Google Earth Engine. He's Álvaro Moreno Martinez. He's working in the University of Valencia. We have different type of projects together with Google and other type of projects. And he's still here in a very small picture because he's also collaborator in the material of this course. He was here last year in the previous time, and this year we needed to split. So in that case, I decided also recognize his work in the slide. So first of all, we need to know why exists Google Earth Engine. And at the end, we would like to observe the Earth. We would like to obtain different type of products from Earth observation satellites. And there are a lot of different type of Earth observation satellites. There are different type of sensors. There are different type spatial, temporal, and radiance resolutions, which are different areas, different timings for covering the same point of the Earth, and different type of spectral resolutions can be multispectral, hyperspectral. So we have a lot of information, too much. Also, Gabriele before talked about the computer, reduce that quantity of the data that we have from the Earth. So at some point, Engine, which is an application working with this type of high quantity of data that we can get from the Earth. It is focused in a geoprocessing application that is focusing remote sensing and GIS data. And there are two main components in the application. First of all, contain a lot of different type of data collections from different type of temporal series of satellites and different type of products also. And we can use the resource in the background of the Google Cloud Computing. So that provides us a massive computational powerful to process different type of data. I will show you some examples at the end of the talk. At some point, as I commented, you can find Different type of data. For instance, we can focus in Landsat and Sentinel, which are 10, 30 meters spatial resolution, 5 days temporal resolution for Sentinel, 16 days for Landsat, or we can move a little bit in a coarse spatial resolution, which is MODIS, that can provide data daily or in a composite of 8 days products between 250 meters at 1 kilometer spatial resolution. But more than that, we can use vector data, which is also ingested in the cloud. We can also have land cover and terrain products, and we can use weather or climate data. So at the end, it's a huge quantity of data that it is already ingested in the cloud. We don't need to worry about put our data or not. The official products are there, are connected with the different agencies in order to be ingested on the Google Cloud, and we can use directly using the application. If we would like to use data that it is not already ingested in the cloud for whatever reason, you can ingest your own data in a very easy way, okay? Not only the official catalog is available, also there is a secondary or a parallel data catalog was developed by another Google developer expert, which is the Airwasham GE data catalog. It's also available in the link, and in that catalog you can find a lot of different type of data too. In that case, are more focused in final products that the scientific people developed and ingested in this catalog. In this case, I don't know the quantity of terabytes that is already in this catalog. So that makes that at the moment that Google Earth Engine started, of course, very few publications were related with it. But over the time, I start to increase a lot, because at the end, if you work focus on remote sensing, and if you work focus on GIS data, it's a very easy application that there are negative things, I can say, I'm not going to lie to you, but in most of the cases, there are a lot of pros to use it. Sometimes before, I'm going to say, before we need to worry about different resolutions of the different sensors that we use it at the same time when we work it in a local computer. Nowadays, with the application, we need to worry it, but not too much, with the different resolutions that we have in the different data. So working in a multimodal or multi-sensor way is quite easy compared than before working in our computers. Also, as we have the powerful of the cloud, we can do things that before we couldn't do it or require long time for processing. So in that case, are really good. For this reason, also, the quantity of academic research manuscripts increased a lot from the beginning of the Google Earth Engine. If you would like to interact with it, if you would like to play with it, you need to go to Google Earth Engine. I submit the link this morning. I don't know, how many of you do you have already account? Okay. So the people that don't have it will be nice if you have for this afternoon and play with me at the same time. In this case, you go to the link, and here now is something like that, I don't remember. Started or get started here in this part of the, and then you could register. You can register as academic research, then you don't need to pay for the application use. If you go from, if you come from private companies, in that case, you need to go for the commercial service, and of course, in that case, you need to pay. As I commented you before, there are two different ways to interact with Google Earth Engine. We can use JavaScript application. In that case, of course, you need to use JavaScript programming language. It's not so complicated, I can say. The difference is to work between JavaScript and Python. If you see code from one, it's not complicated to try to play with the other. The good point of the JavaScript application is that they have the web development. So has a very fancy Windows, have a very fancy map, has a nice console that gives us the errors, and also the visualization of our results is super easy in that case because everything is prepared for that. But has limited processing because it's a web application, and at some point we need to pass by our browser, so we have that type of problem. I can say that in the opposite, we have the Python application. In that case, 15 years of the use of Google Earth Engine, there are different packages that improve a lot the visualization of the results. There is specifically one package developed by another Google developer expert that is called GMap that provide the possibility to visualize our results in Python. Of course, I can say it's not working exactly the same than the JavaScript application, which is developed already in the environment. Is faster and has some pros compared than JavaScript in the way that when you would like to produce an operational script, it's better to do it in Python. That for them there are not too much difference internally between the two applications. I'm going to focus a little bit more in the core concepts of the application. We need to know that we work with objects at the end, and there are different objects. I'm going to show in this slide the 4 main objects when you work with remote sensing or GIS data. But you have much more than these ones, of course, but I think it's important. One case is the EE image. As you can see, you can load one image with different information, different bands. That is the bands, and the values that you can see here is when you click in one specific pixel of the image and you get all the values. So in that case, you can see that you can have as a band reflectance values, you can have quality flag, you can also integrate NDVI, I don't know if all of you know the meaning, but it's a vegetation index, okay? And you can integrate different information in the images as a band, okay? And it's one specific object that has specific functions for them. You cannot use another type of functions for other specific objects to the image, to the EE image. As the same that we have raster data, and we can load raster data, we can use vector layers, we can use geometries, and they are called EE.future. In this case, I represent a dot, but you can have a geometry, you can have a line, you can have a polygon, a multi-polygon. There are different options of that. And the same, when you click in the point, you can see all the properties and all the information that you have related as a database associated to that geometry. In this case, you can see, for instance, the latitude and longitude where the point is, and you can see the EVI value. EVI is another vegetation index, and you can see the values that are contained in the database. But we can have image collections. So I can load 2 different tiles from Sentinel-2, and I can visualize the composition of both of them. In this case, we have the image collection of 2 different tiles, but take care because we can have temporal series. So we can have also in the same area, in the same area, different information about different acquisitions over the timing. That type of objects are called, is called EE.image collection and has specific functions. You need to take care with that because a lot of people try to use image functions using an image collection or in the opposite, and you get an error. And usually, not always the error that provide application is really clear. So in that case, it's good point to know that first thing that you should look is which type of object I am using and which type of function I'm using. Because in most of the cases is that you try to apply functions from the image in an image collection, okay? We will see how we can do that because it's doable to do that, okay? But later. In that case, when you click in a temporal series, for instance, you can see all the temporal profile. This one is very specific for the JavaScript application. We will see how to produce this temporal chart in Python during the practical session this afternoon. But it is not so easy as I click in my map because we need to use other things. But we will see. And the last object that I present in this slide is the feature collection. As the same that I had one point on the top, I can have multiple points in my vector layer. And in that case, I can have a table with the different values that I have in the different points, the latitude, longitude, and the vegetation index that I had before in one feature. Same here. Take care with that. If you are using functions for features, don't apply to feature collections because you will get an error or in the opposite way. So what we can do with Google Earth Engine, we can get an image collection, we can filter, take out the cloud, we can average, we can apply a statistical value, and we can get an image for a specific study area. In that case, it's a very simple example, but you can do much more, of course. You can do different things. But I think it's very visual animation that clarify what you can do with the image collections. In order to do things, in order to apply operations to the different data that we can have in Google Earth Engine, we have different type of functions. As I commented before, take care, because we have image objects or image collection objects. There are specific functions for image and specific functions for image collections. But there are 4 core functions which are very important in order to work with Google Earth Engine. One is the map function, which is the equivalent of the for loop when you work in a local computer. We should try to avoid use for loops in Google Earth Engine, because when you use for loops directly, you decrease the powerful of the cloud. In that case, the cloud cannot work well, and then you lose that powerful because it's working image by image. In that case, we use the function map, and we will see how we can apply the function maps in the image collection. Another core function are reduce. As the example before, I showed you an image collection that we filter and we reduce in a statistical function. We zoom all the images, or we promediate all the images, or we take the maximum value of the images. We are going to do that operations with the reduce function. Another important is the filter, of course. I commented, we filter the clouds. We need to know how to filter clouds in an image collection, or we can filter considering specific values. I would like to filter the images that I have in an image collection that, I don't know, have a specific name in the orbit. You can do that with all the information that we have in the metadata of the images. You can apply the filters to the property of the metadata of the images, so you can filter your image collection considering that. And the last core function, which is very important, is we can produce a lot of information, we can produce a lot of products using Google Earth Engine, but sometimes we wanted to have it in our laptops because we don't have access to internet at some point. I don't know, but in Europe we don't think on that too much. But if you travel to other countries out of Europe, you can have internet connection problems. And then you wanted to access to your data and you cannot at some point. It's not available in that case. You can export your results to your local computer, so you can use them in that case. You can export images, you can export future collections, you can export, that's all. And you have 3 ways to export data. You can export directly to your Drive account, so take care with that, because you can imagine what is started to happen when you produce a lot of results. Do you? Sorry? Get out of space, and then you can have the option to pay and you need to take care if you don't want to pay too much. Let's say something like that. We can export in that case is free 250 gigabytes approx, and you can export directly to Google Cloud. Take care also with that option if you don't want to pay. Every time that you use the Google Cloud for storage or for processing, you are going to pay. So if you export to Google Cloud, means that probably you need to pay, okay? But there are more functions, as you can see. I'm not going one by one in the slide, no worries. But considering that you can find functions to do traditional machine learning models, as can be random forest or support vector machines, you can use different functions to transform in your image. For instance, you can reproject your image in a specific projection. You can change the scale of your image to another different type of scale. So there are different functions to do that. And there are others which are focused in the future transformations. And there are much more than I put it here in the slide. What we can do, we can have one image, we can have another image, and we can zoom all of them. When you work in a local computer, you use this symbol for zoom images, isn't it? Or zoom data, isn't it? You are not going to use that one because it's a local language. We need to use the function of the Google Earth Engine in order to zoom images, because these 2 images, if we load from the repository of Google Earth Engine, are cloud images, are not in our computers. The application doesn't understand this zoom. We will see during the practical session how we can do that type of things, okay? But you consider that you need to look for a function that is going to zoom or add 2 different images at some point. We can apply a map function, as I commented before. This is a very specific function that is doing the for loops in the cloud. You don't need to type for by one image at some point. You have your image collection. You have your function already defined, what you wanted to do in the image collection, and with the map function, you are going to apply the function that you defined previously to the image collection. So at some point, you can calculate, for instance, the NDVI, which is an image function, it's not an image collection function. You can apply, calculate the NDVI for each image in my image collection. And in that case, you are going to get the same image collection with the NDVI. You can get only the NDVI you can add the NDVI as a new band in your images inside of the image collection. There are more examples. For instance, not only calculate vegetation index, you can apply map to features in order to calculate the area of each feature if you have polygons. You can calculate or filter, well, not filter, you can calculate the cloud cover in each image, or you can make timing compositions. For instance, every time that you use Sentinel-2 in one specific area, and you filter by clouds, at some point, not every day you have an image, because some of them are full of clouds. So in that case, you can make compositions, weekly composition, monthly composition, yearly composition, depending on which type of application you wanted to do. The other function is the reduce that I commented before, is apply statistical functions to our image collection. Or also, if we have different areas covering by the image collection, we can get a composite of the whole study area. We can also use the reducers in order to train a classifier. We will see that Google Earth Engine are working with images in order to classify or in order to predict, create models. So in that case, we need to transform our image collection into an image if we would like to use the temporal information. There are a lot of revisions. You don't need to know all of them. I'm going to show you how to find the help and the information of the functions. But of course, there are 8 specific ways to reduce in Google Earth Engine, depending on if you are working with images, image collection, future, or future collection. But there are more than 40 functions in order to apply different operations. We can calculate the maximum or the mean of our image collection. We can do a linear fits, for instance, using, or linear regressions. There are different types. We can calculate the histogram also in our images in order to know, for instance, how many pixels we have for a specific class, if we have a land cover image, for instance. So we have a lot of possibilities in order to work with it. We can reduce, if we have one image, we can apply the reduce only between the bands of the image. So in that case, we get only one band with the final value, an image with one band with the final value. But we can have an image collection, and we can apply the same function, the sum of the top 3, provide the image of the bottom, okay? And in that case, you can note that the 3 bands that we have in each image are replicating the results. We have the result of the 3 band. The statistical function that you apply is working per band when you work with an image collection. We can reduce considering regions. Maybe we need to know the value of a vegetation index in a specific polygon. So we can do also that. And we get a dictionaries in that case. We don't get images or we don't get features. We get, in this case, dictionaries, which is another type of object of Google Earth Engine that I didn't comment it before, because it's a standard object in the programming language. In that case, I imagine that all of you know a little bit about the dictionaries. And we can have an image with different bands, and we can get the information and have, instead only one geometry, one feature, we can have a feature collection in that case. So if we reduce applying the image, we can get the information of all the bands in the specific regions, applying one statistical function. You have the references, the link is in the slides. There are a lot of information here. I never read it all, so but you have information. You have the information how to install the Python package in your own laptops in the guide reference. You can have the information of the JavaScript, Python, and also I didn't comment it, but also there is a REST application, so you have all the information there. I will show you later with a practical session where you can find this information. Let's put it together, all what I say. So we can have an image. We can choose projections, resolutions, the bands, how we would like to visualize our bands, the bounding box of our image. We can apply a function, whatever function. We can define a function and apply. We don't need to use the functions already defined in the application and apply to the image. We can have our image collection. In that case, we need to decide time range from when to when we are going to load. From Sentinel, we can load from 2015. But if we choose Landsat, Landsat has different type of sensors and satellites. At some point, 1972. So you need to define the time range that you wanted to use, the study area that you wanted to use, and also you can use the metadata information in order to filter the images in the image collection that you initially load of the cloud. You can apply an algorithm there. You can calculate the vegetation index. You can zoom images. You can average images. You can make whatever with the image collection at some point. But how these things are working? Because I talk about the different functions. I talk about the different data that we can find, but I also talk about the application, but I didn't say anything how is working the application by itself. So it's using a directed acyclic graph. That means the application at the moment that you ask something, construct a graph. You have different operations in the nodes and the different links of the operations, what is needed in each operation as a branch, and create the graph. But until you don't say print, export, show me, or whatever, the cloud is doing nothing. It's lazy, as humans, more or less. It's totally lazy. I can load Sentinel-2 from 2015 till 2025, around all the world. I can calculate my vegetation index. I can use all the temporal information, training a classifier, inference the classifier, and the cloud is not doing anything until I say, print, give me something. I need to call from the cloud to my computer what I want. And in that case, is the moment that the cloud starts to work. In that moment, the cloud, once has the graph, because it's already done, start to analyze the different nodes, start to analyze what is important in each node, and start to do the different process and load the data. But you could notice that I put the graph in an opposite way at some point. Instead, I started loading the data and give me the results, which is at the top. And this is because the like that. First of all, I'm going to put an example to explain that. I would like to visualize the maximum value of the NDVI composite of Landsat images from the 2016 year. In that case, I say I wanted to visualize. So this is my first node. Is what is important? Visualize the NDVI, the maximum of NDVI. But at some point, I need the maximum NDVI. What is the maximum NDVI? I need to calculate that. Once I have that step, the cloud is thinking, but how can I calculate the NDVI and how can I add this information in my images? Then I need to filter to the year that I wanted. Once I filter to the year that I wanted, the cloud loads, so construct the graph in the opposite way. That doesn't mean that work in the opposite way. I didn't tell print, I didn't tell give me, I didn't tell export. At the moment that I say export, print, or whatever, the cloud, once the graph is already constructed, provides you the information, okay? So here I'm going to show you now some notable examples that are produced using Google Earth Engine. For instance, the most known product is the tree canopy cover product, was developed by Hansen, and is a global product of the deforestation and how is gaining the forest over the wall at 30 meters spatial resolution. So you can imagine the quantity of data that you need to move there. Also, you can find water bodies maps or surface waters in the cloud, which is also a product obtained using Google Earth Engine. And also, you can see different type of products of the intertidal floods developed by Murray in 2019. But I'm going to show you a little bit one of the examples that I developed in collaboration with Alvaro. Some of them I did it by myself, of course. In this case, we created a gap-filled algorithm in order to produce reflectance data free of gaps. So this is the original time series of Sentinel-2 for the year 2020 in that area of France. And we developed an algorithm that transformed the data, something like that. The scale, the temporal resolution in this case was 5 days. And we could obtain, using the Sentinel-2 images, Landsat and MODIS information to merge them and obtain the gap-filled reflectance data. Another of the products is related with a project that we have already with Google, which is Banks-Flux, and is producing different type of carbon flux at different scales. In this case, we were focused on ground primary productions at 30 meters spatial resolution daily over the continuous United States. That one also, this one is not the ground product, this one is the leaf area index. This is another vegetation index that you can find in the paper that I reference there. In the project, we would like to obtain GPP products as the same that we obtain in the leaf area index. And the last example that I show you is the spring onset. In this case, was a work that I developed in collaboration with the ITC in the Netherlands, with Raúl Zuritamila. And we can provide when the spring is started in the European continent and the American regions. In this case, the maps contains 1 kilometer spatial resolution, are yearly information. You need to consider that in order to produce each map, we need to use the information of the maximum and minimum temperature, daily temperature, over the year, and the number of pixels that we move were kind of 7 million pixels. So the quantity of information that we use it in order to produce this type of maps probably was not possible to produce on our own laptops. I put some references. As I noted, and I heard a lot of Spanish speakers, I didn't want to delete that you have the information in Spanish, but for the non-Spanish speakers, you have also an English book focused on Google Earth Engine. Was published in 2019, and it's a really good book. I read it, most part of it, at some point. And it's very interesting because it contains examples and contains different information that you cannot find in the guide user of Google Earth Engine. So with that, I don't know if I was too fast. No, it was good. As I commented you before, I prepare, as you told me that Python is your programming language, we prepare an introduction to Google Earth Engine in Python. We have also an example to develop biophysical parameter retrievals in Python. As the same that I showed you the maps of leaf area index, we are going to produce maps of leaf area index and to see how we can produce that with training samples already prepared, of course. But you can get the main idea how to train in an inference a model using the application. And if we have time, because not sure about it, if we have time, I'm going to show you what is the continuous change detection and classification algorithm, which is already implemented. I put it here in Python. You need to know that there are things that we cannot do in Python. And one thing is obtain the parameters of the algorithm is complicated to get in Python. It's really complicated. So I decided to show you just that part of code in JavaScript, and we will see how to work with that in Python, okay? But I think that we will see that this afternoon. I'm not sure now, until what time I have?
Until 1 p.m. now.
Yeah. Okay. So let's start this afternoon. I don't know if you have questions or, yeah?
Just one thing between QGIS and Google Earth Engine, where you can see advantages versus disadvantages of using Google Earth Engine or QGIS.
You can use Google Earth Engine using QGIS. There is a plugin. Yeah, you install the plugin, and then as the same that you load data in Google Earth Engine, you can load the data in Quantum GIS. Yes. Also, I didn't comment it, but if someone is better programmer in R, there is also a plugin in order to use R programming language. I don't use it before. I don't know how easy it is to connect it or not in that case. Yeah. More questions?
Yes, so slide 18. Slide 18.
18?
Yes.
Almost there? Here?
Yes.
Yeah.
So I want to ask about the overlap regions. What would happen in the final output?
If you are applying a function which can be sum the images, in the overlapping they sum the different values of the image with the other one, and when there is not overlapping, take the value of the image that are there.
They don't mean it.
Sorry?
They don't do mean. They just sum it.
No, depends the reduction function you apply. If you apply sum, you get the sum of them. If you apply the average, you average them. If you apply maximum value, gets you the maximum value.
More questions?
Hello. One of the function is classification,
Yeah.
right? And for that, you need a reference map.
Yeah.
You do it yourself, or that Google Engine provides you a reference map in any area? Because maybe I want to fly over Santiago and classify the city, but I don't have the reference map, right?
You have two options there. You can create your own training data if you want, or apply unsupervised classifiers, in that case as clustering. If you don't have any information, depends what type of classification you wanted to do. Because, for instance, there are products of land cover. There is a dynamic wall that contains 7 main classes. You cannot classify crops because there is not crop information of them. But you have the class crop, you have the class forest, water, so 7 main classes, and you can use them because you can load this data. You have also from ISA wall cover, I think it's called a map, which also contain, sorry if I'm mistaken, I think that you have more than 7 classes, and you can load the information of them, and you can use that classes. But if that type of data don't adjust to the final classification that you wanted to do, you need to provide by yourself.